In the last section, we were solving differential equation of the form mdx plus ndy equal to 0. When we get a differential equation of this form, we first check whether the given differential equation is exact using the necessary and sufficient condition dou m by dou y equal to dou n by dou x. So if this is true, we will find that this differential equation is exact, and then we can apply the solution integral mdx, where y is a constant, plus integral terms in n without x dy equal to constant. So this is a solution that we can use for exact equation. So if the given differential equation is exact, then we can apply this solution. And in cases where the given differential equation is not exact, we discuss the concept of integrating factors. Integrating factor is a function, can be a function of x and y. When multiplied with the differential equation, we convert the differential equation into an exact equation. So we discuss various rules to find integrating factor. The first rule was by inspection. So here we just rearrange the differential equation or multiply or divide the differential equation with something. By inspection, we find that function that needs to be multiplied or divided, so that we can integrate the differential equation separately and find the solution. So if you have confusion, you can we solve many questions. Many differential equation was solved using the concept of rule 1. So you can go and check the old videos to get a clarity on the topic. So rule 1 was by inspection. Then we discussed rule 2. It was a special case where the differential equation was homogeneous. So if the differential equation is homogeneous, we can use the integrating factor 1 by mx plus ny. So this was rule 2, and rule 3 was a special case. Rule 3 was a special case where the differential equation was of the form f1 of xy, function of xy, into y dx plus a function of xy into x dy equal to 0. So if the differential equation is of this form, we can find we can say the integrating factor is 1 by mx minus ny. Then we discussed rule 4. In rule 4, if 1 by n into dou m by dou y minus dou n by dou x is a function of x alone. Say we call that function f of x. So in that case, integrating factor is given by e raised to integral f of x dx. So this is rule 4, and rule 5 was when 1 by m into dou n by dou x minus dou m by dou y is a function of y alone. Say f of y. In such cases, we use the integrating factor. We say integrating factor is e raised to integral f of y dy. So these were the 5 rules we discussed in the earlier videos to find the integrating factor. So as I mentioned before, if you have any doubt in any of this rule, you can go to previous videos. We have done enough questions based on each rule, and you will have a better clarity and understanding then. So now in this video, we are going to discuss the last rule, rule 6, to find the integrating factor. So once from next video, we will solve some problems based on this rule. And once that's over, we will move on to the next section, which is linear differential equation. So this is the last rule, rule 6, to find integrating factor. So our equation is in the form mdx plus ndy is equal to 0. And this rule applies in a specific case when dx plus ndy is equal to 0 is in the form x raised to alpha into y raised to beta into mydx plus nxdy equal to 0. So in such cases, we can say the integrating factor is x raised to km-1 minus alpha into y raised to kn minus 1 minus beta. So here k can have any value. So once we get the differential equation, we identify alpha and beta. Now, and any x raised to k minus 1 minus alpha into y raised to kn minus 1 minus beta with k having any value will be an integrating factor for this equation. So from next video onwards, we will be solving some problems that uses this rule 6. So before going to that, there is another form in which question can appear which uses this rule 6. I'll just discuss that. Let me get a new page. So this is the form. If the question appears in this form, x raised to alpha, y raised to beta into mydx plus nxdy plus x raised to alpha dash, y raised to beta dash into m dash y dx plus n dash x dy equal to 0. So if the given differential equation is of this form, we have to, we know that this part can be, the integrating factor for this part can be found out by using rule 6, which is integrating factor is x raised to k alpha minus 1, sorry, x raised to km minus 1 minus alpha and into y raised to kn minus 1 minus beta. This is the integrating factor for this part. And for this part, we have our integrating factor as x raised to k dash m dash minus 1 minus alpha dash and into y raised to k dash n dash minus 1 minus beta dash. So we have two integrating factors for the two parts of the differential equation. So if you find k and k dash such that km minus 1 minus alpha equal to k dash m dash minus 1 minus alpha dash and kn minus 1 minus beta equal to k dash n dash minus 1 minus beta dash. So if you use these two equations and solve for k and k dash such that it satisfies this equation, we can find this either this or this. The integrating factor becomes a common integrating factor for both parts. So it becomes the integrating factor for the whole equation. So if you have doubt regarding this, we'll be solving problems based on this concept. So we the rule is just identify alpha, beta, m, n, and alpha dash, beta dash, m dash, and n dash. Write these two equations, solve for k and k dash, such that this condition satisfies, and then write our integrating factor as x raised to k minus 1 minus alpha or into y into kn minus 1 minus beta, which will be equal to k dash m x raised to k dash m dash minus 1 minus alpha dash and y into k dash n dash minus 1 minus beta dash, because these two are equal. Okay, so we'll be using this concept to solve problems. So this is rule 6, and just going through the rules once more. Rule 1, rule 2, rule 3, and rule 4, and rule 5. So as I mentioned, we'll be solving problems using rule 6, and after that we will take up the next section, which is linear differential equations. Thank you.